In 1984, a catastrophic gas leak in Bhopal, India, killed thousands of people in one night. What if a single design choice could have drastically reduced the scale of that tragedy? It turns out there was one, simply storing less of that deadly gas on site. This idea of removing or reducing hazards outright is at the heart of inherently safer design, or ISD. Instead of adding more alarms and safety gadgets, the first step is to eliminate the danger at its source. Now, let's break down what inherently safer design means in practice. Every industrial facility has three layers of safety measures. The first one is inherent design features. The other is engineering controls, and the third is administrative control. Inherent safety is the first and most fundamental layer. It's all about designing the process or plant so it's fundamentally less dangerous even before add fancy engineering safeguards or procedures. As a rule of thumb, if you can get rid of a hazard entirely or replace it with a milder one, do it first. Only after that should you rely on engineering control like relay valves, dike, or alarms, or administrative control like procedures and training. So, how do engineers make a design inherently safer? There was four classic strategies. The first strategy is substitution. Use less hazardous material or reaction when possible. For example, if a toxic solvent can be swapped for a harmless one, that substitution cuts out the risk at its roots. The other strategy is minimize, means reduce the amount of dangerous substance in use or storage. Smaller volumes mean a smaller accident. This was the missed opportunity in Bhopal. Storing huge quantities of methyl isocyanate gas created a colossal hazard. The third strategy is moderate, means use milder condition, lower pressure, lower temperature, or more dilute mixture, so that any release or failure is less severe. The next strategy is simplify, means design procedures to be as straightforward and error-proof as possible. Complexity can create unexpected failure mode or human errors. Simpler systems are often safer by nature. These principles might sound abstract, so let's consider a concrete example. Take the Bhopal disaster mentioned at the start. The plant was storing about 40 tons of a highly toxic volatile chemical methyl isocyanate in large tanks. When water accidentally entered one tank, a violent reaction overpressurized it, and a massive toxic gas cloud rolled into nearby neighborhoods with devastating effects. An inherently safer approach would have been to avoid storing such a large inventory of methyl isocyanate at all. In fact, after Bhopal, many companies did exactly that. They changed their processes to produce hazardous intermediates just in time and in smaller quantities, so that a runaway reaction could never release tens of tons of poison. So by minimizing the stored quantity of a dangerous chemical, the worst case scenario shrinks dramatically. As safety guru Trevor Kletz famously said, what you don't have can't leak. Another example, some manufacturing plants have transitioned from using toxic substances like chlorine gas to safer alternatives like bleach solution or UV treatments for water purification. This substitution eliminates the risk of chlorine gas releases to the surrounding community. No chlorine on site, no chance of chlorine leak, inherently safer by design. Inherent safety is not just about chemicals, either it can apply to any hazard. If a platform is high in the air, gravity is a hazard, people can fall. If you can design the operations so that heavy work is done at the ground level instead, you've eliminated the fall risk rather than relying on harnesses or railing. If a reaction generates a lot of heat and pressure, an inherently safer design might be to find a catalyst that lets it run at ambient temperature and pressure. Eliminating the extreme conditions that could lead to an explosion or a crisis is the target of inherently safer design. The beauty of inherent safety is that it tackles problems proactively, not reactively. Instead of layering on multiple safeguards to control a large hazard, you strive to not have the large hazard in the first place. This matters because all those add on safety features, alarms, relay system, training, and other are prone to failure or human error. But if the hazardous material isn't there or is present only in a small amounts, even mistake won't result in catastrophe. Think of it like this. Driving a car at 200 kilometers per hour requires excellent brakes, airbags, and seatbelts to manage the high risk. But if you design a car or set a rule that it simply cannot go above 50 kilometers per hour, you've inherently made the situation safer. A crash at 50 is far less deadly than a crash at 200 kilometers per hour. Even if all the fancy safety devices fail, it was just an example. Modern process safety standards strongly emphasize this approach in facility siting and layout design. Eliminating and reducing hazards comes first in the hierarchy of safety controls. Only when inherent safety measures are exhausted do engineers move on to adding engineered safeguards and administrative rules. It's a bit of a mindset shift. Rather than asking, how can I handle this large danger safely, we ask, do I really need this large danger, or is there a safer way altogether? In summary, inherently safer design is about building safety into the DNA of a facility. By substituting for less hazardous material, or minimizing the quantities we store, or moderating operating conditions and simplifying design, we greatly reduce the chance of a disaster from the very start. The lesson for safety and operations experts is clear. Always look for opportunities to design out hazards before relying on add-ons. If you remove the ball from the china shop, you don't have to worry about how strong the teacup are. In practice, this means during project design or hazard review, challenge each hazard. Can we eliminate or reduce this? Often, the most eye-opening safety improvement come not from adding more protection layer, but from realizing a layer wasn't needed in the first. Because the hazard can be eliminated. The practical takeaway is that the safest plant is the one that inherently poses less danger. Start there and you won half the battle of process safety.